All right, everyone. So for our first talk today, we have Luke Oeding, and he will be giving us the second part of tensor decompositions.
Okay. Well, I was trying to get a head start on the day today because we stopped before I got to tell you about tests for border rank or expected rank for tensors. So let's just go and talk about this for a second. So the first thing we mentioned that I mentioned in the discussion after the lecture last time is that we had this subspace variety, which is the variety in which of tensors for which you can use less tensor coordinates and up to change of coordinates. And that always contains the rth secant variety of the Segre product. So the border rank R tensors always have the r plus 1 by r plus 1 minors of 1 flattenings vanishing on them. And you can think about other types of flattenings where I collect more than just one vector space at a time. And I think that was Professor Sternfeld's question motivated by that. There's much more interesting things to know when you collect more than one vector space on one side of the flattening. So a lot of people have worked in this area, so I tried to collect some of the names. So for the second secant variety, Garcia, Stillman, and Sternfels conjectured that the 3x3 minors of flattenings suffice to define this variety. And that was proven in many different cases by Landsberg, Manivelt, Wayman. Claudiu Raicu has the most refined version of this statement and proved the full force of their conjecture and also a generalization of their conjecture. With Mateusz Michalik and Piotr Zurnik, we also described a lot of the local properties of this variety in any characteristics. So the point is that the second secant variety, the border rank 2 tensors, are defined by all the 3x3 minors of the 1 and 2 flattenings. So you actually need sometimes to collect 2 of the vector spaces on one side of the flattening and not just only one vector space on one side. Okay, but then what happens when flattenings run out? Flattenings are not the end of the story. So when flattenings run out, a recent result of Yang-Chi is that the third secant variety of any number of factors of the Segre product is defined by the equations that you might have expected, well, the 4x4 minors of flattenings, but also you need Strasson's degree 4 equations, and if I have a moment at the end, I'll describe more what these equations are. So it turns out that 2 classes of equations define the third secant variety. So then we look at the fourth secant variety, and things get a bit harder. As far as I know, we don't know a lot more for general n in more than 3 factors, but in 3 factors, again, several people worked independently and together on this variety. There was a big conjecture or a question by Elizabeth Allman on this variety as well. So Landsberg Manivelt made a huge reduction. Friedland made a very big progress. With Jan Bates and myself, we used Bertini to make another step in this direction, and then Friedland and Gross also made a big contribution to
Probably the most important name there, though, is Strawson.
Strawson, yeah. Let me not forget Strawson. His name will show up in a second. So this variety is defined, the fourth secant variety of a triple Segre product is defined by 5x5 minors of flattenings, Strawson's degree 5 equations, Strawson's degree 9 equations, and somewhat possibly more mysterious is Landsberg and Manivel's degree 6 equations. And as a set, those are it. So the point is, like, maybe as an ideal, the ideal may have more equations in it that are necessary, but we don't know that yet. But at least these equations suffice to tell you precisely when you have border rank 4 for a triple Segre product. So these equations, these are pretty straightforward. These are found by representation theoretic methods, much like what Christian Eichenmeier was talking about in his talk. Okay, so that's how you can check at least the lowest border rank for non-symmetric tensors. Okay, great. So let's go back to the beginning of last lecture, where I had everyone whose birthday was in September say tensor, and whose birthday was not in September say something else. So here's my recollection of what happened. So somebody said donut, somebody else said bagel, someone else said coffee, and someone in the audience said tensor. Right? And what I heard was just the amalgamation of everything. And the goal of today is going to be to describe how to add redundancy to the picture so that we can actually recover what everybody said in the room. Okay, that's our goal. So it turns out that what we did is we said, well, I really want to say tensor a lot of times, etc. And I'm going to repeat all the other words several times. So this is a communication scheme inspired by CDMA technology, which is code division, multiple access cell phone technology. And in Pierre Camon's lab in France, they actually are interested in this type of tensor decomposition, which is often called Oeding decomposition. So the idea is treat each signal, say L1 down to L sub R, the R people that spoke, as a linear combination. So this will be, say, A1 x1 plus A sub n x sub n. And this next one, L2, will be B1 x1 plus Bn x sub n. And the last one will say be C1 x1 plus Cn x. And as we know, if we add several vectors together, there's no way to recover the sum ends, right? If I add two integers together, you don't know, and I gave you the result, you don't know what integers I started with, right? So the trick here is to say tensor many times. So we're going to raise each one of these guys to the dth power, and we're going to send this. So we're going to send dth powers, and then what we're going to receive is going to be this linear combination of the Li to the D. And our goal, so why is this called Oeding decomposition? Oeding, maybe 400 years ago, was interested in solving this problem for integers and prime numbers. But we're interested in solving this problem for polynomials. So this is going to be our, say, f, and then try to recover the Li uniquely. So that's the goal. That's what we're trying to do. So naively, what I've set up here is a very large system of polynomial equations of degree d on r times n variables. Right? So the ai, bi, ci are variables or parameters. And then the x's are just going to be thought of as placeholders. And I have many degree d equations. For instance, what is the coefficient on x1 to the d over here? Well, on one hand, it's f1111 is equal to, well, all the ways that I can get x1 to the d out of all of these summands, right? So it's a1 to the d plus b1 to the d plus c1 to the d. Right? That's my first equation that I have to. And then what's f21111? Well, this is all the ways of getting a 2 and the rest 1. So a1 to the d minus 1, a2 plus b1 to the d minus 1, b2 plus of this c1, d minus 1, c2, etc. So this is how you write down the system of equations that you would have to solve in order to find these things. Okay, so we all picture. So if you get bored during the lecture, try this for plane cubics. Can you solve this problem for plane cubics? So the last time I checked, using Bertini and 50 processors, this took on the level of 1 minute.
So solve this problem means recover the A's, B's, and C's?
That's right.
From the F's.
From the F's. So I'm going to give you, somebody, see the thing here is I'm not going to give you random F's. I'm going to choose rational numbers, A's, B's, and C's. I'm going to raise these forms to the dth power, so I'm going to cube them all. And then I'm going to send you the resulting coefficients. And I want you to try to recover A, B, C, and D.
And R is relatively small.
And R is going to be small. Like, so take R, say less than or equal to 3, for instance, in this case. But maybe you want to even worse, try all the way up to R less than or equal to 5. Okay, so Bertini can solve this problem. It's great, right? It's just a straightforward system of equations. But 1 to 2 minutes on 50 processors may be too much computational time. Okay? And you can imagine how this is going to grow as soon as we go to maybe a couple more variables and a little bit higher degree. It's going to be very hard to solve this problem. We're going to try to solve the first instances of this problem much faster than this, maybe by hand. Okay? The first instances of the problem. Okay. There are other methods that you can also use, alternating least squares. You can try to estimate. Just a couple of things before we jump into the algorithm that I have prepared to solve this problem. I just want to give you a little bit more of what to expect for these problems. So again, we have the expected dimension. Expected dimension of sigma r of nu p pn. So this is the Zariski closure of all of the polynomials of the form L1 to the d plus L r to the d, such that Li Rn Cn plus 1. Okay, so this variety, well, if you're just doing a parameter count, well, I have just re-embedded Pn, so I didn't change the dimension. I'm going to choose R points from that. So I have R times n. And then I choose a point on the secant plane spanned by those. So this is the expected dimension of this guy. But it could also be the dimension of the ambient space. Okay, so that's the dimension we expect of this variety. So that means that we expect the max rank, the rank, expected rank is just this ratio. If you work it out. Okay. So this is what we expect the rank to be for these varieties. Okay, and maybe if this isn't an integer, we don't expect a fractional integer, so pick the right integer just next to this one.
What did you write next to n plus 1?
Let me write it again.
Good. Good.
This is the dimension of the ambient space divided by the dimension of the variety. And then I subtract one from both. Oh, sorry. Sorry. N plus 1, no R. So R goes here. R is roughly this. Okay. Okay, but this could fail. So why did I say expected rank? And I said last time that for the Segre variety, arbitrary number of factors, we don't know exactly when the expected rank is the actual rank. We don't know if the expected dimension is the expected dimension. Let me just point out that Alexander and Hershowitz, around 1995, solved a 100-year-old problem that this dimension is correct, except for when it's not.
Since you wrote it with a tilde, it's correct except when b equals 2.
Yeah. Well, anyway. So this dimension is correct except for a small list of examples, and I don't want to dive into all of the examples when it's not correct. So there is one infinite family. There's about 5 or 6 sporadic cases when the expected dimension is not equal to the actual dimension of this variety, and if you're interested in looking at the details, please look at maybe Ottaviani and Brambila's paper has a shorter proof of this that you could look at. Okay, the last thing about what to expect. So this is what I should use when I'm designing my communication scheme is I don't want to try to use more people I don't want to allow more people to talk then I can actually recover their signal. And the rank needs to be less than or equal to this number. So I'm going to choose D, depending on the number of people are speaking, n minus 1 or n plus 1, so that the rank is less than this number. So when the rank is less than this number, I expect to have finitely many decompositions. Let me tell you why I expect finite decompositions here. So I need the incidence variety. So usually it's called an incidence variety because it's much more general than this, but it's also called the abstract secant variety. So abstract secant variety is just the variety where nothing can go wrong. So it's called by cursive I. It's just the pair, the triples P, well, multiples x1, x sub r, such that P is in the span of the xi. Langle-Wrangle is span in this talk. Okay, so this lives inside of Pn, so x is in P capital N. This is inside of P capital N cross x r times. It always has the correct dimension. So the dimension of I is just equal to r times the dimension of x down plus r minus 1. Just count parameters. It always has the correct dimension. And, well, why is this important for the uniqueness of Waring decomposition or of tensor decomposition? Well, we're going to use just very basic algebraic geometry. I have a projection onto the first vector, which projects to the rth secant variety of x. And if the dimensions agree, then the fiber is zero-dimensional, generically. Okay, so if the dimensions agree, the variety upstairs has the same dimension as the variety downstairs, then generically, of course you can probably find some fibers for which the dimension, or the fiber is positive dimensional, but most of the time, with probability 1, you'll have finitely many decompositions of your given tensor as long as you're in the low border rank case. So for more on this story, there's several authors in the last several years, 2002 to 2006, and maybe also more recently, 2014. There's Mella, Chiantini, Ottaviani, Dalico, and a very long name, Van Ruvenhoven. I have to look at the, well, let me not write all of his names, sorry. Van Ruvenhoven.
So this is smooth already, the incidence variety?
Well, it depends on if x is smooth, right? So if x is smooth.
Oh, if x is smooth, then it will be
then
smooth.
it's just the Cartesian product of all of these things with this one instance.
No, but it's, I mean, the incidence variety.
I have to think about it, I'm not sure, because this
Probably
incidence
it will be
maybe
smooth
causes
if
some
x
singularities, right?
It will be smooth when it's.
Okay. So there's several people who worked out all of the possibilities that the theme here is if the rank is subgeneric, expect finitely many decompositions.
In other occasions where I've seen this, it's always smooth.
They also have something to say about when the rank is generic, but since we get to decide our communication scheme, let's just stick in the subgeneric case, and we don't have to worry about the rest of it. Okay, so Now I'm going to talk about how to find the decomposition. Is there any questions about, any more questions about this?
The rank is sub-generic?
Yeah, so if the rank is less than generic rank, or the expected rank,
So in these finitely many cases?
then there should be finitely many decompositions. But there could be exceptions. So again, one of these beautiful theorems in algebraic geometry. What you expect is true, except when it isn't. And the small cases when it isn't are all beautiful and interesting.
You're saying let's stick to the small list?
Yeah, there's a small list where this can fail, and they tell you what the list is. We also recorded the list in a paper that the Togliani referenced in the first lecture.
So, okay, you're saying stick to the small list or stay away from
Stay away from the small list. Yeah. Stay in the case where everything is as you expect, right? Because we're going to hopefully someday talk to the engineers and help them design a better communication scheme, and we're going to give regular behavior, right? We don't want these like one special case that we have to handle separately. We want everything to be regular. So stay sub-generic and avoid this list of the possibilities.
Well, if you stay subgeneric, then you only have to avoid equals 2.
So, there's very few cases you have to avoid. So let's start talking about some very old mathematics. Sylvester's algorithm. So there are a couple of ways to decompose a tensor, and apart from the sort of brute force polynomial solving, all I know is that they're all based on this algorithm. So it's very important to understand Sylvester's algorithm from around the 1850s in this range. So the first thing, let me give you a little bit of tools that we're going to need. So we're going to work for binary forms. So if we're given, say, L is equal to alpha x plus beta y, then we're going to define the polar L perp. It's going to be minus beta partial x plus alpha partial y. So my partials and my alphas and betas, I'm sorry if they look very similar, so just ask me if you can't read something. So this is going to be in C2, and this is going to be in C2 star, the dual vector space. So I'm explicitly naming a basis of each one of these vector spaces. And there are dual bases because partial with respect to x and y are dual to x and y. Okay, and then for some polynomial f in degree 2, we have the fundamental theorem of algebra, right? Or in two variables, I mean. So if we have a function in SimD of C2, well, there's two things that we can do. Is one, we know it completely factors. So I want to do this inside of the dual space for now. So this is always factor. So it's always of the form L1 perp, L2 perp, L to D perp. This is a fundamental theorem of algebra. So now I'm going to do what we did with regular tensors that have no symmetry. I'm going to perform a flattening. So I have a symmetric flattening. These are also, well, I'll name the other names in a second. So okay, so if I have f is a degree d polynomial, I can write down the following matrix associated to the polynomial, which should remind you of flattening. So I'm going to label the rows and columns by I and j multi-indices, and I'm going to take d by d x I plus j in general, but we only have two variables here. So I can make this even easier in this case, right? So let's just find little I and little j on E multi-indices. Okay, let's try this. Okay, that would be in. So if I have x and y, this is what I'm going to do. I'm going to take derivatives with respect to x and y of degree d. And don't worry, I'll give you an example if the notation is just a little difficult. But anyway, I'm going to take all possible partial derivatives. And this matrix, if you notice, it only depends on, this is also a Hankel matrix. And it's also known as a catalecticant matrix. So Sylvester was quite the poet, I guess, and he would use poetry terms to describe some of his mathematics.
But it should be either d minus e or e over the y, not d.
Okay, let's see this in an example in a second. Sorry, I want to say the theory first and then do the example. So what can I do with this? Okay, so here's the main proposition that's going to make all of this work. Okay, so let's suppose L1 to LE are distinct. And then there exists some constants, say lambda I and C, such that this has a solution. So this happens if and only if, this statement happens if and only if f factors, sorry, f is annihilated by these factors. Okay, so this proposition, if you haven't seen it before, well, it ends up being essentially just a dimension count plus this statement that we wrote right here. So this is not a difficult proposition, but it is what makes everything work. So what's the point? So the point is, if some polynomial p is in the kernel of this map that we just wrote down is general, well, first of all, it's a polynomial in two variables, homogeneous. So it factors, and it has this property that it annihilates f. So it factors p is L1 perp up to LE perp, and p f equals 0. So we can use the kernel of the catalecticant map or the symmetric flattening map to tell us the linear forms in the decomposition of our given polynomial. So in the previous lecture and in the very beginning of this lecture, I mentioned that flattenings tell you the border rank or the expected rank for a given format of tensor. Well, flattenings also tell you how to decompose the tensor as long as the rank is really small. So let's do this in an example now that we have all the theory on the board. Okay, so here we're going to do a binary cubic. And I picked one ahead of time with good coefficients, so hopefully everything will be clear and not too messy on the board. Okay, so this polynomial is the sum of two cubes, and we're going to find those two cubes. Maybe you can guess them because, I mean, the numbers are really nice. I picked integers ahead of time. But let's just walk through the algorithm, okay? So compute the catalectic at map. So this catalectic goes from sim2 C2 star to C2. And let's write down the flattening with labels. So d by dx, d by dy, dx squared, dx dy, dy squared. Those are the labels from the matrices, and let's just fill in all of the entries. Maybe you notice the Hankel structure. Okay, so if I computed all my derivatives correctly, this is, maybe you don't like really big matrices, so this is 6 times 9 minus 1 minus 1, 27, 27, minus 1, 24. Okay. You good with this? So I made a couple of choices sort of implicitly in the way that I'm doing this, but they're all consistent. So, okay, so the next step is to compute the kernel of this map. Anybody really good with linear algebra already know what the kernel of this 2 by 3 matrix is? Well, if you didn't, I already computed it. So the kernel of CF is the span of minus 5, 9, 2. But this is inside of sim2 C2 star, so it's actually equal to this polynomial. Okay, so I rewrite my integer vector as the integer coefficients of a polynomial of degree 2 and 2 variables, and then I factor it. And you should not expect this to factor over the integers, but I chose this as a nice example, so it would. So okay, so this polynomial then factors, and then these are the polars to the linear forms that I was looking for, so I need to swap them. This means that f, my polynomial, is equal to some constant, I guess I was calling it lambda, lambda 1, times the polar of the first form, which is swap the coordinates 2x plus y cubed plus lambda 2 x minus 5y cubed, and then set coefficients equal and solve a linear system for the lambdas. So I don't know what the lambdas are, but I just solve an easier linear system, and I get lambda 1 equals lambda 2 equals 1 in this case. Okay, so it doesn't have to be 1, 1. Again, this is just for the exposition. Okay, so I found the decomposition. Let's walk through it one more time. So I start with my polynomial. I compute the symmetric flattening of the polynomial as a matrix. That matrix has a kernel most of the time, as long as the rank is not too large. So I reinterpret the kernel as, again, a polynomial, and I factor that polynomial. And then I use the factors, I polarize them, and I get linear forms in decomposition. So there's an extra bonus. So John asked if anybody remembered the cubic, the formula for the roots of a cubic. So I've actually just given it to you. So let's solve this cubic equation. Solve this cubic equation, f equals 0. So we just wrote it, f is equal to 2x plus 1 cubed. So I'm going to dehomogenize just for the sake of what we're used to seeing. Set y equals 1. Okay, so if I have this, it's the sum of two cubes, then this means that 2x plus 1 cubed is equal to minus x minus 5 cubed, but then this means that 1 is equal to 2x plus 1 over minus x plus 5 cubed. Okay, so omega cubed equals 1, then we have x equals 5 omega j minus 1 over omega j plus 2. Okay, so now you know how to solve a cubic equation. There's no formulas to memorize. There's just the Sylvester algorithm to solve a cubic equation in one variable. Okay, so any questions about Sylvester's algorithm? Because we're going to jump into eigenvectors of tensors and more sophisticated algorithms in a second.
So can you just just run through the statements again, just quickly to say, so you have some binary form. Can you just run through maybe the slide with the red?
Oh, okay. So I start with my binary form, and this proposition is telling you why the kernel, the factors of the kernel actually give you the linear forms. Okay. So it says that if I compute this matrix, right, the kernel is a subset of polynomials over here. But these guys all factor because of the fundamental theorem of algebra. And moreover, they factor as the product of polars of linear forms, just by working in the dual basis. So the proposition says that this product here annihilates my form. So I'm looking at this is in the kernel of the catalecticant map, if and only if this is satisfied. So the proof of the proposition is just compute the dimensions of the two vector spaces involved.
So you choose E. So you write down this matrix, you choose the rank.
No. The matrix determines the rank for me. So it could be that the kernel is empty, then I just stop the algorithm. I can't say anything else. In fact, if you pick a generic rank form, this is probably going to happen to you.
I would think of it as you start, say you want to start cheap and write it as A. Well, so let's go to sum of 2 cubes, then you do this sim2 to simd minus 2. That is a kernel, you use the algorithm. If that fails, you go to sim3 to d minus 3, and you keep on going until you get a kernel.
So if I hope that I will have time at the end to state a theorem which tells you precisely when this algorithm works and precisely when the next algorithm works. But I just want to make sure the algorithms are clear, and then we'll say the bounds.
What does failure mean? So
failure means this form. Well, in this case, the way I set it up, this map always has a kernel, right?
Yes,
so
exactly.
and I can always work through this. But maybe, you can imagine if there are more than 2 variables, then the polynomial won't factor. They won't have any solutions over the rational numbers, for instance, or even over complex. You can also imagine when the degree is higher, we get a square catalecticant matrix, and it still has no, and then it has no kernel.
May I make a comment?
If you think remarks that if the degree is odd, right, then if you set the degree to be always 1/2, it will be always one-dimensional at kernel.
Yeah, that's the last statement I'll make. I'll just maybe let me just skip ahead and I'll tell you this theorem. So I'll just tell you when this algorithm actually succeeds.
I wanted to make a comment. If you think of this in terms of Macaulay's inverse system, you know what it is, and to associate it to the cubic, we have a Gorenstein ring in 2 variables, a 0-dimensional Gorenstein in 2 variables, which is a complete intersection. So there's 2 generators. You look at the smaller degree generator, compute that. If this generator factors as a polynomial in distinct eigenvalues, then we can do it. If not, we have to go to the higher degree generators, and a general linear combination of the lower and the higher will give you the presentation.
Good. So there's a huge commutative algebra interpretation of these things, which is super interesting. I'm trying to stick just to the most basic matrices and so on, but this is exactly true, what you said. Good point. So here's the theorem, and I should attribute it mostly to Rubino and Kenneth, but we made a small improvement. So they have a nice book on these type of methods. So the catalecticant algorithm, or Sylvester's algorithm, succeeds well when in the following cases: 1, if D is even, and R is less than or equal to M plus, okay, so M is equal to N plus M, N minus N minus 1.
What's N?
N plus 1 equals the number of variables.
What is the binomial coefficient? Sorry, there is some R and N.
This is, what does succeed mean? Does that mean assuming you can factor the polynomial, or?
Okay, so I'll give you the full statement. Okay, so let's let the I equals 1 to R, Li to D equals F general among of rank R. And then set Z I is the line through the i's, and capital Z is the collection Z1 to ZR. And then M, I guess I want to round this. Okay. So this should have been ahead of time, and I'm about to finish the statement, but I haven't completed this sentence yet. Okay, so if D is even or D is odd, and R is less than or equal to N plus M minus 1, which is N, with no extra subtraction, then the kernel CF, the most square catalecticant, is equal to the ideal of degree M vanishing, the ideal of polynomials of degree M vanishing on Z. So this is subspace of degree M polynomials vanishing on the set Z. So the kernel is actually equal to the polynomials which vanish on the forms we're looking for, and the algorithm succeeds with Z is equal to Z prime, which is the zeros of the kernel of CF. So, sorry, the statement is really long because it's really technical, but the point is supposed to be that as long as the border rank, or the rank R, is less than this number in the even case, or less than this number in the odd case, then the algorithm will finish.
But this assumes you know how to find the zero-setter collection of
Well,
polynomials.
we translated a hard problem to not quite as hard problem, but still a hard problem. Right? I mean, you still have to solve this system of polynomial equations, but it's a smaller system than the one we started with. So there's one other case. What could happen that you may have more points than the number of forms in the decomposition. So another thing that could happen is if D is even and N is greater than or equal to 3, and R equals N plus M, choose N minus N in this case. With this, then the algorithm the algorithm succeeds, but so Z prime is going to be the zero set. It's written over there, but it's small. Okay, so the zero set of the kernel of the catalecticant map could be larger than the number of points that you want, but it's still finite, and
So is that the zeros of the kernel?
Yeah. forgot the word kernel.
Thanks. Okay, so I go through my algorithm, I compute this kernel, I compute the zeros. It could be that I have more zeros than the number of forms in my decomposition. I'm sub-generic rank, so I know that I should expect a unique decomposition. And after finite linear checks of subsets of these points, I could find the decomposition.
So
Okay.
that never happens in this first case? And if R is less than this number?
So I'm
then-
taking away the 1, right?
But in this case,
In this case, you exactly get the same number of points in the zero set as the number of forms,
as R.
as R, yeah.
So I guess the point is this cuts the degrees of the equations you need to solve in half, and how it reduces it depending on what R is, I guess. So I don't know.
Yeah,
for the
R
naive
is-
algorithm, I could see the degrees are double, but I don't see how many equations.
Well, the number of equations depends on the size of the kernel,
Yeah.
right? So you should expect the kernel, in fact, in this case, you just pick a generic element of the kernel and it factors. But in the other cases, you actually have to solve a big system of linear equations. So it's best to just check these things in practice. I think, like, just implement it into your computer and see what happens, okay? So we did this. You can download our Macaulay 2 code off of the ancillary files in the archive attached to our paper. So if you're interested with Giorgio, we wrote all of these things in Macaulay 2 just to see what's really happening. Okay, so now I want to sort of switch gears a little bit so that I can describe the best algorithm that I know
Your
Just
question.
to
about-
make
okay.
sure I understand this. Here you're taking the Li, when you say general of rank R, that means Li is a sort of generic independent.
Yeah, we're trying to avoid some interesting or pathological cases where, there are a couple of cases here maybe that this could fail. But as long as I avoid a Zariski closed set, then it's going to be true.
And what's the running time, or where does the energy, is it efficient?
So I can't tell you the efficiency of this algorithm. You just have to check it on the computer, okay? Like I didn't do a complexity analysis of the algorithm.
Something you have to solve.
You have to do some work sometime. But as long as the rank is small, you hope that
So
you can
do we end
actually...
up solving polynomial equations, or
Yeah, but it depends how many variables. I mean, in two variables, you just have to factor a low-degree polynomial. So that's clearly easier than the naive. In more, you have to find the zero set of a collection of polynomials. So it's like your original question, but they're lower degree, and I think there are fewer equations as well. So your life is slightly less miserable.
Okay, so let's hold the rest of the discussion until after, if that's okay. Next topic I want to talk about is eigenvectors of tensors. These were invented in around 2005 by Lim and independently by Key. And there's been since a lot of work on spectral theory of tensors, and I just want to introduce this because it's a key to the next algorithm for decomposing symmetric tensors. So let's just recall matrices, just so we know. Let's suppose I have a matrix that goes from a vector space to V, linear map, and I have V inside of V, and I have lambda inside of my field. Then the eigenvalue equation is MV is lambda V. We all know this. I can also eliminate the need for the eigenvalue, which my colleagues in linear algebra don't necessarily like this, but I'm going to do it. This is the same thing as saying that MV and V point in the same direction. So this is the same way of thinking of an eigenvector, but you eliminate the eigenvalue, which may or may not be a good choice. Okay, so with polynomials, then let's take some polynomial and some V of V. So how do I define an eigenvector of a polynomial? Well, here's the most straightforward way I know how to think about this. So I'm going to do the first flattening. And maybe Jam doesn't like this, but I'm going to say V is V star. So just ignore all the stars in the picture. So this will be a way I can define an eigenvector. The C1p of V, now I can eat something of degree d minus 1 and spit out a vector in V again is some lambda V. If this happens, we say V is an eigenvector of P with eigenvalue. But I could also ignore the eigenvalue and just write C of eating V d minus 1 times, wedging with V and eating 0. Okay, let's compute an eigenvector of a polynomial. Let's suppose I take the product of 3 variables and just try this one. So here's C1 of P. Okay, so I'm going to label x, y, z, and then I'm going to label these guys x squared, x, y, x, z, y squared, y, z, and z squared. So those are my labels of my matrix. And then the only places I get a 1 in the matrix are when x, y, z occurs. Okay, so that's my flattening matrix. And now I'm going to eat v1x plus v2y plus v3z squared. And I get a system of equations. So this is C1p eating this guy, right? So this is also equal to v1 squared, v1, v2 with a 2, v1, v3 with a 2, v2 squared, v2, v3 with a 2 in front, and then v3 squared. This vector, okay. Is it clear? I just used the variables x, y, and z to hold places, but then I square this out, and this is the vector I'm actually feeding my matrix. So I get a system of equations now that I have to solve. So if I'm going to have C1p v squared equals v times some lambda, then this means that I have to have 2v2 v3 equals v1, 2v1 v3, v2. This is the way I decided to solve it. 2v1 v3. And I'm just going to set lambda equal to 1 for this problem. Okay, so the solutions. Well, maybe you can see right away that I need vi to be equal to plus or minus a half. And then some of the signs are going to work and some of the signs are not going to work. So there's, check the signs. So I could either have v I, Vj, and Vk be all plus. I could have a minus, plus, plus. I could have minus, minus, plus, and I get a minus, minus, minus. So the system's completely symmetric. This collection of signs can work, and this collection of signs can work. These two collections of signs cannot work. So this is 4 solutions. So 1, 2, 3, 4.
So this is for eigenvalue 1.
Eigenvalue 1.
There's also 3 solutions for eigenvalue 0.
Good. I picked eigenvalue 1 for this. Okay, so now you might want to know how many eigenvectors are there for a given tensor. So Temi Kolda asked this question to Bernd and his student at the time, Dustin Cartwright, and they were able to answer this question using toric geometry. And here's the answer. So theorem, Cartwright. The number eigenvectors of a general V of the surface is Cn is this beautiful formula. And then when d equals 2, just take the limit. Use L'Hopital's rule to get the formula. Okay, so we know how many eigenvectors of a tensor we should expect by this theorem. There's also a way to count this by using Chern classes and vector bundles, which Giorgio and I explained in our paper. Okay, so now let me connect in the 3 plus whatever discussion time we need, connect this to tensor decomposition. Okay?
So what do you salvage if you, okay, that number doesn't change, but if you make a change of coordinates, so the identification of V with V dual changes.
I just did that to write down a nice example. You don't need that identification.
Oh, so this is a well-defined.
It's a well-defined thing. Without, I just wanted to write a clean example of the not a lot of discussion about duals and non-duals.
Okay.
Okay. So here's an example. Hilbert quintics. Okay, Hilbert quintics. So Hilbert, Valentini, and Rosen said the following theorem. They're old enough that we don't have to write their names. So a general F inside of sim 5 of C3 has a unique decomposition.
So in a question, so this example, we didn't have a general P, so I don't get 4 if I plug it into this formula.
You get 7 in the form.
7. Was 7.
So there are 4 eigenvectors for eigenvalue 1 and 3 with eigenvalues.
Oh,
Seven.
okay. Okay. Thanks.
In the next example, we will get the full 7.
Mm-hmm.
Okay, thank you. A general plane quintic has unique decomposition as the sum of 7 fifth powers. And unique means up to the obvious rescaling and reordering. Okay, so I want to give you an algorithmic proof of this statement, but also like how to decompose a plane quintic. And if you think the algorithm is just limited to this one case, no, I won't have time to discuss all the cases for which this algorithm works, but let's just follow what we should do. So step 1 is just check the catalecticants. So what are the sizes of the possible catalecticants that I can have here? Well, they're going to be sim 3 of C3 star to sim 2 C3. This is a 6 by 10. This cannot detect rank 7. So the Sylvester algorithm will fail, guaranteed, for this general form. Okay, so step 2. So Ottaviani generalized Strasson's equations to a larger class of equations called exterior flattenings, also called Young flattenings in Landsberg and Ottaviani's paper. So these are new equations, and they're going to also provide the key to finding decomposition. So what we're going to do first is we're going to twist the catalecticant by the Cozul matrix. So let me remind you of the Cozul matrix I care about. K is going to go from C3 to C3. And the first Cozul matrix you may have learned is this one, 0, x, y, z. Put a minus sign here, 0, 0, minus x, y, minus z. Okay, this beautiful 3x3 skew-symmetric matrix depending on 3 variables, x, y, and z. So what's the twist? The twist is I'm going to take K twisted. So now this is going to be CP2. Well, the 2 is implied, so I'm going to erase it. It's too messy. So what I'm going to do is I'm going to take the derivative with respect to whichever variable here of the form P, and I'm going to write the block matrix CP. So let me write the matrix, and then I'll say dimensions and so on. This is C partial x P, negative C partial y, C partial z, 0, C partial x, C partial y, E, C partial z, 0. Where C partial x P, for instance, is from sim 2 to C3 star to sim 2 to C3. So this is a 6x6 matrix. And then I have a 6x6, 3x3 matrix with 6x6 blocks. So this is 18 by 18.
What is twisting here?
So the twist is sort of really twisted, right? So I'm taking the x here, and I'm taking the derivative with respect to x onto the p, the polynomial I'm starting with. So I'm twisting the Cozul, the catalecticant matrix by taking a derivative of the form before I form the catalecticant matrix. Then I'm collecting all the possible ways of doing that into this block matrix, which is looks skew-symmetric, and since the blocks are symmetric, it is skew-symmetric. So we know that an even-sized skew-symmetric matrix has determinant is a square. It's just the Pfaffian, right?
This is the definition. That's the definition.
So here's the facts. So 1, K circle P is linear in P. So this implies that if P has rank, well, I need one more thing. In 2, if P has rank 1, then K circle CP has rank 2. So these two facts imply, with the subadditivity of matrix rank, that if rank of P equals R, then rank of K twisted with this twist is less than or equal to 2R. Okay, so I made this bigger matrix, and it may not have helped me any, but what I've done is I've tripled the size of the matrix, but the rank of the matrix only goes up by double from what the catalecticant case does. So I get a little bit bigger range for which I can detect the rank of the tensor, and it turns out that, so in this case, if P has rank 7, then K twisted CP has rank less than or equal to 14. So this means the 16 by 16 Pfaffians vanish. And also I have a 4-dimensional kernel.
Probably what the P has border rank.
So I can work past to the closure. So if it has rank 7, it's true. If it has border rank 7, it's still true. Okay, so I have a 4-dimensional kernel. But now let's look at what this kernel is. So what are the spaces in which I map from? Where is this map going? Well, I did a twist. So K circle CP is a map from sim2 C3, so our tensor C3 now, to sim2 C3 tensor C3 star. I left the star out over here. This is star. Okay, so I just told you I have a 4-dimensional kernel in this map. And the kernel is then this space here. So this space is a space of the kind of polynomials for which I know how to compute the number of eigenvectors right here. So a general element in this kernel has 7 eigenvectors, and then the key observation is that these eigenvectors are the linear forms, are the Li in the decomposition. So this is the thing that we proved in our paper, is that in general, if you start with, again, a low rank polynomial, first try the catalectic algorithm. If that doesn't find the rank for you, and if it fails, then try the Cozul algorithm, the exterior flattenings algorithm, which is take a Cozul matrix, use it to twist the catalectic matrix by taking partial derivatives and blocking the matrix, compute the kernel of that matrix, then compute eigenvectors of a general element of the kernel, and as long as you find a finite number of eigenvectors, generally you will from this formula, then you can find the linear forms in decomposition. Again, computing these eigenvectors is a hard polynomial problem, but it's not as hard as the original problem that we started
So in
with.
particular, the eigenvectors don't depend on what element you take. The entire
It should be general, yeah.
The entire
exactly.
four-dimensional space has a fixed set of
That's right. That's right.
General element.
And the reason why I was taking this wedge product is we also form something slightly more general when we have exterior powers instead of just copies of C3. So we can define a slightly more general type of eigenvector, and we also count the number of those eigenvectors which we needed for this algorithm. Okay, so I've overused my time, but I hope that clearly explains. Thank you very much.
Okay, so we still have a couple of minutes for some more questions for Luke.
Yeah.
So you've taken sort of these original large system of equations which have very high symmetry structure to them and reduced it down to a smaller set of equations. Do you know of other applications where you can use this? Does it work for general tensors instead of symmetric tensors?
So that's also the topic of current research.
Okay.
Can you do exactly the same algorithm, but what does it mean to do that for a symmetric tensor? So John said, you have a system of polynomial equations that have a lot of structure, and can you solve other problems with this kind of idea? So yes, I think we can, but we need to try it. By the way, this algorithm is also implemented in Macaulay 2 and takes a half a second to solve this problem if you start with rational numbers on one computer, not with 50 processors. So, if I had time to write on the board, I could write an 18 by 18 matrix. We could have done it by hand, actually, if we started with the rational solution. So, yeah.
So for certain NMD, you used this to show that there was the 7, you can get the 7 sum of 5th powers. For more general NMD, does it have any analog to the arithmetic?
Yeah, so the other case that we can solve that sort of demonstrates where this is working is Sylvester's pentahedral theorem. So, yeah, I'm sorry I didn't have time to explain all of it, but if you have ternary cortex, we can also solve ternary cortex. So quaternary cubics of C4. In this case, the general form is the sum of 5 cubics. And Sylvester had a pentahedral method for solving it a long time ago, but now this algorithm works. But we actually need to consider, for sim3 v, we first lift this to v tensor v, and then we lift again to v tensor wedge 2 v tensor, it's complicated, v star tensor v. And then our Cozul map ends up being a map, this K circle C ends up being a map like this. V star tensor wedge 2V to V star tensor V. And when we construct this map, we now need eigenvectors of tensors that are of the following form. They're of the form sim D V, tensor wedge A V of this type. And we can also compute the number of eigenvectors of this type as well by a similar Chern class formula. So we actually needed it for the Sylvester pentahedral equation theorem to do the decomposition. So slightly more general than what Lim and Chi defined, but very analogous.
So people who actually do this in practice, in numerical practice, they use iterative methods for finding eigenvectors and decompositions. Do you see a connection? Has this been explored, how this might tie in with iterative methods for tensor decomposition?
So I think the place for iterative methods, so I actually did this in MATLAB for the Hilbert quintics, is that write down all of these matrices now in MATLAB so that you can compute the kernel numerically. Now I have a general polynomial here, but it won't have all of the nice rational properties that I had before. But I could still try to use a power method to find the eigenvectors here. So I would like to try to do something like I iterate just m times v, compute the norm, divide by renormalize, and keep going, or keep iterating. And I think that's the place to do it. Is when you're trying to find the eigenvectors of this kernel, general element in the kernel, you should then apply numerical methods to find it, because we don't expect to have a rational solution to the eigenvector problem. So I think exactly at that place is where we should use the iterative methods.
All right, let's thank Luke again.